Hello everyone. Today Grace and I will be talking about orthogonal contrasts. We will be explaining more in depth what it means for contrasts to be orthogonal. We will provide an example of an orthogonal contrast. We will explain why this is a desirable feature in experimental design. And furthermore, we will explain why it is a desirable feature for design matrices specifically. So let's get into it. What does it mean for a contrast to be orthogonal? Well, to clarify and review, a contrast is essentially a linear combination of two or more factor level means with coefficients that essentially sum to zero. So knowing this, an orthogonal experiment in experimental design is orthogonal if each factor can be evaluated independently of all the other factors. So a contrast is orthogonal if the sum of the coefficients in each linear contrast sum to zero. Furthermore, the sum of the products of the corresponding coefficients in any two contrasts must equal zero. So here we have an example of an orthogonal contrast. You can see here on the left-hand side, we have four different contrasts at 5 levels each. If we want to determine if contrasts A and B are orthogonal, we will sum the product of each treatment coefficients between A and B. So what does this look like? This looks like by multiplying 1/3 times 1, 1/3 times negative 1.5, and so on and so forth, and summing them together. Here we can see from the calculation that I did that they do indeed sum to zero. Therefore, we can say that contrasts A and B are orthogonal. So why is this a desirable feature? Well, orthogonality is a desirable feature because number one, it simplifies the least squares calculations and moreover causes the covariance between any two contrasts to essentially be zero. If we take a CRD, for example, with two factors, we know that the sum of squares for the model is equal to the sum of squares of factor A plus the sum of squares for factor B plus the sum of squares for the interaction between factor A and factor B. This is similar to an orthogonal experiment. If we look here at the example I've provided on the left, if we sum the product coefficients between contrast B and contrast C, we can see that they do indeed equal zero. Therefore, there are contrasts. But if we look at the sum of squares specifically, similar to the CRD, if the model contains terms per se A, B, and C in that order, then both sums of squares for C represent the reduction in the sums of squares of the residual error that occurs when C is added to a model containing both A and B. And just to review, the sum of squares for a model term, especially in ANOVA, partitions out the variation due to the term after accounting for variation due to earlier terms in the model hierarchy. By knowing this information, we can further clarify the sum of squares model for this orthogonal experiment specifically by saying the sum of squares of B plus the sum of squares of C is essentially equal to the sum of squares of the model. And this is also because the degrees of freedom for B plus the degrees of freedom for C is equal to the degrees of freedom for the total model. That is why it is a desirable feature in experimental design. Now, Grace will be further illustrating this point by showing an example of how orthogonality is a desirable trait for design matrices.
Now that we have a little bit more background on what it means for a design to be orthogonal, now we're going to be moving into answering the question of why is it desirable to have the design matrix be orthogonal. So to start off with, we're going to be looking at example 7.2, which had a 2 to the 3 design with 8 treatments. And the first order model is that y hat is equal to beta hat 0, which is equal to your intercept, plus beta hat 1, x1, plus beta hat 2, x2, and finally plus beta hat 3, x3. And then below that, I've written out the design matrix. So the plus ones on the left column correspond with the intercept term, and from there to the right, you can see that that corresponds to the beta hat 1 and so forth. So now that we have the design matrix written out, we can take individual columns and look at their cross products, because in order for a design to be orthogonal, the cross product of any two columns has to equal 0. So for example, let's take the first two columns, which corresponded to the intercept as well as beta 1 hat. And so looking at this, you can see that there are 4 positive and 4 negatives, which equal 0 from the cross products. So therefore, we can conclude that this design is orthogonal, and the parameter estimates will be independent, which will be helpful to estimate later on. Now that we've looked at an example where the design matrix is orthogonal, we're also going to consider the alternative, which is that the design matrix is not orthogonal. And so in this example, we have a 2 to the 2 design with the full quadratic model written out. So y hat is equal to beta hat 0, which is your intercept, plus beta hat x1, plus beta hat x2, plus beta hat x1, x2, which is your interaction term, plus beta hat 1, x1 squared, and finally beta hat 2, x2 squared, which is your second quadratic term. And so looking at the design matrix for the full quadratic model, we can see that on the left side, the plus ones correspond with the intercept, and these are the same as the last two columns, which are the quadratic terms. Now we will do a similar analysis to what we did in example 7.2, and we'll be looking at the cross products of any of the two columns, because if the design is orthogonal, then the cross product should be equal to 0. So now we'll be taking the first column and the last column, which corresponded to the intercept and one of the quadratic terms. And so as you can see from the cross products, this does not sum to 0, so we can conclude that the design is not orthogonal. And the main issue arises because the columns are indistinguishable, and so this creates confounding between the x1 squared term with the x2 squared term. And overall, after looking at these examples, orthogonal designs are very important because it allows for the parameters to be estimated independently of one another.